Okay, I think there are some other questions in the chat, but I think let's take them later on. I think it's good to start some Piazza discussions, and we'll have some discussion sessions also where we can discuss some of these questions. We're going to talk more about memory controllers and quality of service issues later in the course also, and some of the solutions that are suggested, like compiling an application to better make use of the memory scheduling policy. I think those are really good ideas, but unfortunately they're not done today because people don't even compile for caches today, even in many cases, and memory controller happens to be so far away from the processor from the current design perspective that people don't necessarily even think about compiling. But that's a very good idea. And it's good to discuss it going into the future. And there's also, in my opinion, there's a very good opportunity for making memory controllers more programmable as well. So maybe you cannot compile your application to what the memory controller is designed for. Maybe you cannot increase your row buffer hit rates fundamentally, right, for whatever reason, because you don't have good locality, and it's very hard to get the locality in your application. But what you can potentially do is instantiate a policy in the memory controller, assuming your memory controller were programmable. That policy would be matching your application nicely, your memory access patterns nicely. So I think this sort of exploration is going to be a lot more important going into the future as memory controllers become more and more intelligent. And we are toward that path right now. How do you design memory scheduling policies that are more application specific or customized for different applications' memory access patterns is a very good research direction. And again, it's very hardware-software cooperative. You cannot do this without knowledge of what's going on at the higher levels of the software, how you're accessing data, what are your access patterns, what is important and what is not important in terms of access and computation, what you should prioritize, what you should not prioritize. If you have all of that information, and if you can communicate that to the memory controller, then the memory controller can also be reprogrammed or reconfigured to actually implement a policy that satisfies the needs at the higher levels of the software. And that's what we were mentioning yesterday when we talked about cross-layer design. This is an example of cross-layer design that's really waiting to be done. And there's some research that is toward that direction, but there's no research that has shown that this is that has shown end-to-end that this works really nicely. So there are opportunities over here. And what I discussed yesterday, the interfaces, the expressive memory interface, for example, is one interface through which this information can be communicated, but maybe you need something else to be able to do that as well. Okay, so I took that detour before starting lecture 2B. We should really include this part in the previous video. And I think there were some other questions, but I didn't get a chance to read all of them. But please include the discussion in Piazza. I'm hoping we will have some lively discussions on Piazza and hopefully dig deeper as we want to in this course. Okay, so let me cover something similar in nature, in the sense that it crosses abstraction layers. You need to go even deeper in the abstraction layer to understand what's going on. And again, once you go deeper, you have a lot of potential for solutions if you're thinking critically and broadly. And that's the issue of data retention and memory refresh. Basically, all memories have this problem. Whenever you store data into a memory, retention is a problem. You may lose that data, right? That's true for DRAM, as we will discuss. That's true for flash memory, as we will discuss. That's true for tape, as we will discuss. Although some memories are better at retaining data, some others. And this is, again, very broad, right? We store data on different things, right? Even if it's not computers, we used to store data, or some people still store data on books, right? Books have some data retention lifetime, right? If depending on how you keep them. Like 500 years later, some books may actually lose what's written on them because you didn't keep them well enough. Or even if you perfectly kept them, depending on the material with which you wrote onto the book, you may have lost the data, right? So there are data retention issues in all types of memory and storage devices. But we're going to focus specifically on DRAM in this case, and specifically on DRAM refresh. But again, this idea will be applicable to many other memory technologies also. And in the last part, I'm hopefully going to show you that. Okay, so we saw this picture before and gave a different context. Now we're going to focus into this DRAM part and dig deeper into the DRAM. And again, we're going to talk about cooperation between the DRAM and the memory controller as well. So let's go deeper. We're going to break the abstraction layer of that DRAM bank. If you remember that DRAM bank, it had two-dimensional array of cells. And this is one of the cells in that two-dimensional array. And you've seen this before in digital design and computer architecture. If you haven't seen it, take a look at the course. We're going to talk about DRAM cell later on again. But if you want to know about it more, take a look at lectures from last year from digital design. But basically, a DRAM cell consists of a capacitor, which is this one, and an access transistor, which is this one. And this is true for any memory cell needs to have a storage device, which is the capacitor in DRAM, and an access device, which is the access transistor in DRAM. Of course, access device is actually bigger. The access transistor enables access to this capacitor. Basically, charge is stored in terms of, the data is stored in terms of charge in the capacitor. Capacitor can be charged or discharged, and charge state indicates a 1 or 0, and discharge state indicates the opposite value that you encode in the charge state. And to be able to access DRAM, you need to enable this access transistor through the word line. Once you enable the access through the word line by applying a positive gate voltage over here, or enough gate voltage over here, the charge from the capacitor gets shared through the bit line, basically. And you can sense it through the sense amplifiers at the bottom. So now we've gone one layer below the abstraction. We were looking at how the circuit really operates, right? It's not even gates anymore. It's really circuit. And I'm not depicting the sense amplifier. So any memory needs to have some sort of structure like this. Storage device and access device. And some sort of memory array structure to optimize for density. Okay. So a DRAM chip consists of tens of thousands of rows of such cells. So you've seen the two-dimensional array. That was a bank. Basically, a two-dimensional array, a row could be 8 kilobytes, let's say. And the number of rows you may have in a bank could be 64,000, let's say, 64K. That's a reasonable number, for example, for today. Of course, this depends on how much you can pack, what are your latencies. So you can actually do more, pack more. But you can see that this is one row over here. Okay. So what is the problem with DRAM? So DRAM, no memory technology is perfect. It's always a trade-off. There are always trade-offs between different technologies. In DRAM, one fundamental issue is the capacitor charge leaks over time. So let me go back to this picture over here. You have this capacitor. Whenever you need to access it, you actually charge share with the bit line, fine. But if you don't access it, this access transistor is off. Even during that time, because the circuit is not perfect, there is a RC conductance path from the capacitor through the access transistor into the bit line. So the capacitor slowly leaks charge, basically. There are multiple charge leakage paths actually over here, but this is one path over here. So capacitor charge leaks over time, and as a result, you may lose data, basically. If you don't refresh DRAM, meaning replenish the charge inside the capacitor, inside the charge capacitor, you may lose data because the data is stored as charged, and if you need that charge, you don't want the bit flip happening. And the memory controller needs to refresh each row periodically to restore the charge. And this is very fundamental to DRAM. And this means that you need to activate each row every n milliseconds. Typically, n is 64 milliseconds. And there are many different refresh mechanisms that are proposed today. Today, it's not in the hands of the memory controller. So the memory controller, for example, sends a command to DRAM saying refresh, but it doesn't say refresh this row or this row or this row in today's systems. DRAM internally handles the refresh because that's how the protocol works. There are upsides and downsides to this, which we can discuss when we actually need to, if we need to later on. But this is the abstraction that I'm providing to you. There is an activate to each row every n milliseconds, and typical n today is 64 milliseconds. But by the way, this is reducing. In some DRAM standards, today it's 32 milliseconds. And this also depends on temperature, by the way. At high temperatures, data leaks much faster through the capacitor. As a result, you need to refresh more frequently. So at high temperatures, for example, it's every 16 milliseconds today. Okay, but I'm going to assume at nominal temperatures, at low temperature, it's you need to refresh every 64 milliseconds. That's the specification. But of course, refresh has a lot of downsides, right? You're doing this just to retain data. It leads to energy consumption to do the refresh because each refresh requires an activate. And it's not just an activate, it's also a pre-charge after that because you need to refresh some other row or you need to access some other row after that, right? So it's an activate pre-charge pair, and that consumes energy. It leads to performance degradation because the DRAM rank or bank can be unavailable while it's being refreshed. So today, actually, people try to reduce this performance degradation as much as possible, but there needs to be some granularity of refresh at which the DRAM, a part of a DRAM is not available. So this is not desirable. It leads to some quality of service, predictability impact, because you can have pause times during refresh. If a processor is trying to access memory at the same time as a refresh is happening, then the refresh gets priority because you need to refresh DRAM. As a result, this leads to a delay in the processor, latency impact. And also, refresh rate limits DRAM capacity scaling. Now, what does this mean? Basically, as you increase DRAM capacity, there are two things that happen. One is the cells become smaller, and the second is you want to put more rows into the DRAM so that you can have higher capacity. And both of these are actually bad for refresh. Making the cells smaller makes the capacitors smaller, meaning that they can store less charge, meaning that they can leak charge faster. Making the cells smaller makes also a variation higher, meaning that these cells are more subject to noise, and as a result, some cells become much more leaky than before. So I need to make sure that they need to be refreshed often. So refresh rate increases with cell density or cell size. And also, refresh rate needs to increase with the number of rows, because if you keep increasing the number of rows you have in DRAM and you need to refresh at a certain frequency, you need to increase the frequency at which you need to refresh at a certain frequency, let's say 64 milliseconds. And if you have more rows to refresh within those 64 milliseconds, then you need to generate more refreshes to them, right? So that's why as DRAM capacity increases, refresh increases. But before that, let's do some analysis. I actually gave this in digital design also. So if you've done that assignment, you can copy and paste your answers over here. But imagine a system with 8 exabyte DRAM, 2 to the 63 bytes. We're almost there in existing supercomputers. Assume a row size of 8 kilobytes, 2 to the 13 bytes. How many rows are there? So this is a very simple question for many of you. It's 2 to the 50 bytes, hopefully for all of you actually. Basically, 2 to the 50 rows are there, right? How many refreshes happen in 64 milliseconds? Well, that's 2 to the 50 rows that need to be refreshed every 64 milliseconds, right? Oh. What is the total power consumption of DRAM refresh? So I cannot give you a good answer over here, but it's in the order of kilowatts over here. But you need to do this calculation by figuring out how much current is drawn by refresh and calculate the power by looking at the parameters of the DRAM chip. And what is the total energy consumption of DRAM refresh during a day? So you can calculate that once you figure out how much power is consumed by DRAM refresh. And this is a very good exercise because you can figure out how many refreshes need to be done in a day, right? And a day consists of many 64 milliseconds. And this is a good exercise, and I would suggest that you do it. If you can do it, that's great. I'm not going to assign you this one because we've already assigned this in digital design and computer architecture. You can probably find the solutions to it also somewhere online in the digital design and computer architecture solutions. But my point is refresh is consuming a lot of energy, especially if your DRAM size is larger, and especially if your refresh rate frequency is smaller. And this is really wasting energy. There's no point in wasting this energy. And this is one of the potential benefits of non-volatile memory like we've discussed in the previous lecture. If you have phase change memory, for example, non-volatile, you don't need to refresh it. Now, I'm not perfectly correct when I say that, but you don't need to refresh it as frequently as this one, as DRAM. But we will talk about why you may need to refresh it later on when we talk about emerging memory technologies. There are other reasons why you may need to refresh it. But that memory is not charge-based, so leakage is not as fast. So you would gain a lot of energy by not refreshing memory if you could transition to some other memory technology. But unfortunately, other memory technologies have problems, so it's not easy to transition to them immediately. As we've discussed, they have latency issues, for example. So we're stuck with DRAM for some time. I believe actually we're stuck with DRAM for a longer time than people think that we will have DRAM, because DRAM is actually a very, very strong technology, in my opinion. It's very hard to find another technology that provides you the same density and latency characteristics. So it's reasonable latency. Okay, it's always high, of course, latency, but it's reasonable compared to some other technologies. but the density is very high, and we're using it in very good ways today. So DRAM is going to be around for some time, and it doesn't have endurance problems like some other technologies do. So let me depict what we had done in 2012. This is a paper that we wrote when we first started looking into refresh. And we basically said what I just said earlier. As device capacity increases, refresh will become a bigger problem. And this is a good function of an architect, in my opinion. Educate the community about up-and-coming problems in the future. In this case, we said that today, at 4 gigabit devices, DRAM chips, refresh consumes 8% of the time, meaning 8% of the time you cannot access the device because it's doing refresh. Okay, it doesn't sound bad. 8% is still not ignorable, let's say. It's not that bad though. But if the current trends continue, meaning if you don't do anything about refresh, and if we keep increasing the density without doing anything about refresh, this will become a much worse problem in the future. If you have a 64 gigabit chip in the future, it's going to spend 46% of its time refreshing. Of course, it's a projection model. This is a pessimistic projection model. Later, we wrote a paper in 2014 that has both projection models, optimistic and pessimistic. The optimistic model is around 25, 28%, I believe. You can take a look at that paper. It's an HPCA 2014. I'm going to reference it also. But basically, somewhere that's, in my opinion, not acceptable. You don't want to have a large DRAM chip that you're supposed to access and not be able to access it more than, let's say, I don't know, 25% of the time, let alone 46%. 46% is basically saying half of the time I cannot access this chip. That doesn't sound very good, right? Because it needs to do refresh, because it needs to retain data. Okay, so that doesn't sound good. And we said that that doesn't sound good, so we should have some solutions to this problem. So this is part of the problem. Energy is another part of the problem, basically. Refresh causes energy overheads also, as we've discussed. And this is the percentage of DRAM energy that's spent just refreshing. Okay, today meaning in 2012, it's about 15%. Of course, you need to assume some things when you do this calculation, right? Because you need to assume some activity factors, meaning how often are you accessing DRAM? Whenever you're accessing DRAM, of course, a lot of energy is consumed by DRAM access itself, right? But if you're not accessing DRAM, you need to refresh it, meaning that most of your energy is going into refresh in DRAM energy. So for example, my cell phone right now is doing nothing, but it needs to refresh its DRAM. It's actually in self-refresh mode. It's very much optimized. But most of the energy is consumed in self-refresh right now, actually, because it does need to keep the memory active so that when I receive a call or whenever I interact with it, it can quickly give me a response, right? So this is assuming some activity factor, and with some reasonable activity factor assumptions, I believe we came up with the fraction 15%, which is reasonably high, I think. And this becomes worse again if you have a 64 gigabit chip. If you increase the number of rows, if cells becomes denser, so that refresh becomes a bigger problem, you need to do more frequent refreshes. 47% of the DRAM energy is spent refreshing. So we said, again, this doesn't sound good also. You have a DRAM that's nice, high density, but half of the time you can access it, and half of its energy is consumed by something that you're not asking data for. It's really overhead operations. So, okay, now we see at least the high-level trends. The question is, how do we solve the problem? So I'm going to give you a little bit more observation, basically. The observation is that all DRAM rows are refreshed every 64 milliseconds. So one critical thinking that you may do seeing this is, do we need to refresh all rows every 64 milliseconds? And once you ask this question, now you can start exploring many, many potential answers, right? Okay, are there any potential answers? I'm happy to take them. And this could be a very good discussion point in Piazza also, even if there are no answers right now. And I think answers abound here all across the stack. It's a little bit different from the previous problem. I haven't even given you everything over here, right? But there could be software solutions to this also at the high level. Maybe, for example, okay, let me give you a freebie. Okay, there you go. I think I got an answer. Only the one we accessed previously. Basically, you want to refresh only those that you accessed previously. Maybe I don't quite understand this answer, but I would say, let me actually try to. I think we were thinking along the same direction. Basically, only the things that you really allocated and put reasonable data on, right? I would argue that exactly. Yeah, I think somebody also said that. Yeah, I think we're thinking the same way. Basically, you don't need. First of all, you don't need. Let's assume that you have 8 gigabytes memory, but you're using only 128 megabytes of it for whatever reason right now, and everything else is not allocated. Why not just refresh everything that's only allocated? So even that's not done actually today, which is really interesting, because we don't have the interfaces from the operating system to the hardware controller, memory controller, saying that operating system basically cannot tell the memory controller, okay, these are the rows or these are the memory regions that are allocated by me. Don't refresh anything else because I don't really need them. It's very sad if you think about it, right? Because we're lacking this cross-layer design, cross-layer interface. The memory controller is not aware of what it really needs to refresh. And this is a very, very simple thing, right? This is something that's very simple to do. Of course, it requires some more effort, some more storage, but it's not done today. It's a very good idea. So those folks who have developed the ideas, kudos to you. And it's a good idea. It's already published. Unfortunately, you cannot publish it again. But unfortunately, it's not done today because of that. So this is one example of what critical thinking brings you. And it's a sad state of affairs. This is the way it is because there's a huge disconnect between the system software and the operating and the hardware layers today. And maybe in future generations you can actually fix this. But this is exactly why some companies who are designing the software and the hardware together are at a much better position to optimize across the stack. So this is one example. So there could be other reasons actually, and you've taken one. What if we knew happened underneath in DRAM cells and expose that information to the upper layers? So what you said earlier is exposing what happens upper at the software layers, what's allocated, and you're exposing it to the memory controller. That's one direction. And you could optimize things very nicely that way. It doesn't work if all of your memory is allocated. It's a sad part. That solution, it doesn't work. So if you have 64 gigabytes of memory, and if everything is allocated by some application, you're efficiently utilizing your system to the max, that solution doesn't work because you have no room to play with. But there's some other solution that may work in that case, or in every case, if you knew what happened underneath in the DRAM cells and expose it to the upper layers. And let me give you an example over here. So if we somehow magically figured out the retention time profile of DRAM cells, ask the question, how long can this DRAM cell retain data really, truly? You would get something like this. Well, you basically test every single DRAM cell and you would get something like this. So today we're refreshing everything every 64 milliseconds, but that's really a worst case assumption. The assumption is this. The data sheet provided by the DRAM manufacturer says you should refresh everything every 64 milliseconds, otherwise we cannot guarantee data integrity in DRAM. And the memory controller designer or system designer believes this because that's the contract between two components. And they basically refresh everything every 64 milliseconds and done. There is no further thinking or questioning. But if you actually question that assumption, saying, do I really need to refresh everything every 64 milliseconds, you will find out that the answer is no. Because there are some cells in DRAM that can get away without refresh, even tens of seconds actually. Of course, this depends on temperature also. But even at very high temperatures, some cells are very strong. They happen to be store a lot of charge. They happen to be very not leaky. As a result, they can retain data for tens of seconds. But there are also some cells that are weak, very, very weak. And those are the cells that dictate the refresh rate today, because you don't want to lose any single bit. Some cells are extremely leaky, extremely small, and they have to be refreshed every 64 milliseconds. As a result, we set the refresh rate today to every 64 milliseconds. So it's really worst case thinking, which is not necessarily a good thing if you want to optimize a system. It's worst case thinking because we don't have anything, we don't have any other interface, any other way of discovering how often you should refresh DRAM cells today. So it's easy to say, I'm going to refresh everything every 64 milliseconds and every single cell will work. But that's overdoing it for cells that can retain data for 10 seconds. And if you look at this, it's actually kind of proportional, meaning you can pretty much reduce your refresh rate by 4x, in this case, 256 milliseconds, as you can see, and lose data only for a very small fraction of DRAM cells, right? That's the idea over here. So now if you actually, okay, before we go into how we can exploit this profile is very interesting and powerful. If you knew this information, one thing you could do is you could refresh every DRAM row at the rate it requires to be refreshed at, right? Which is really nice. That way you can get rid of almost 75% of refreshes. And that's going to be the idea of Radar, which I'm going to discuss in a little bit. But before we go into that, I've kind of alluded to this, but we should ask the question, why do we have such a profile? It's always good to understand this thing. And the reason is manufacturing process variation. Basically, manufacturing is not perfect. We do not know how to manufacture every single DRAM cell or every single hardware component to be exactly the same. This is true for actually manufacturing anything, in my opinion. But especially at very small technology generations, this manufacturing process variation becomes much higher. Because your control through lithography is becomes very smaller. And actually, there's a lot of research that goes into lithography devices so they can cut things in much better ways, but it's not a perfect thing. So your control is much lower at very small dimensions. As a result, not all DRAM cells are exactly the same. Some are more leaky than others because some may have small capacitors, leaky capacitors, small transistors, leaky transistors, or transistors with less resistance. So there are many, many reasons. And as we've discussed at some point, this is called manufacturing process variation. Okay, so you have this process variation. Can you somehow take advantage of it? That's an opportunity, basically. So assume that we know the retention time of each row exactly. What can we do with this information? Who do we expose this information to? How much information do we expose? And of course, all of this affects hardware and software overhead, power consumption, verification complexity, and cost, basically. Because if you expose a lot of information and it all needs to be correct, you need to verify that your information is correct, right? You cannot say this DRAM cell contains or retains data for 10 seconds. Later, the person who relied on you finds out that that's not true. It actually retains data only for 64 milliseconds. Now you're in trouble. Or everybody's in trouble because you get a bit flip on a critical piece of data potentially, right? That's not good. So you need to verify this. And also, if you expose a lot of information, cost increases clearly, power consumption increases. So there is a lot of things that you need to take into account in terms of how much information you expose and how do you expose it also. And also there's how do you determine this profile information, right? How can you determine it perfectly and accurately? And we're going to talk a lot about this in this lecture because I think this is very instructive in terms of the difficulty of a problem that's conceptually easy. Okay, and also who determines it? It was very, very interesting also. Whose responsibility is it? Is it cooperative? Is it the memory manufacturer? Is it the memory controller? Is it the system manufacturer? So there are many, many things that can be done over here. Okay, so this is actually something that cuts across the stack, frankly. It goes into sometimes even the programming language. So I don't know, maybe we can have a discussion on memory refresh on Piazza. But for example, let's say that you had a very nice compiler. Compiler somehow figured out the lifetime of different objects in your program. And it communicated that information to the hardware. And it encoded this lifetime, let's say, in terms of some time units that can be translated to milliseconds at some point, right? Because compiler can do some of that analysis, right? So maybe conservatively, fine. Maybe it doesn't know everything, clearly, that goes on. But let's assume that it did an analysis conservatively. It found out that there are some data structures that you touch that are not needed for a really long time. They're going to live for very short. They're not going to be allocated to registers. They're going to be allocated to memory. But they're going to live very short in memory, meaning much less than 64 milliseconds. With some assumptions, of course, right? Compiler clearly cannot guarantee exact timing. But assuming that you can translate the lifetime of objects in a way that the hardware can translate into milliseconds, maybe you can take advantage of that profile information that the compiler collected. And this is the lifetime of objects, actually. And actually, many compilers, managed compilers, the Java compiler, for example, or C# compiler or F# compiler, in garbage collected languages, you need to do this anyway. You need to know some sort of lifetime information about objects to be able to optimize well. And if you can communicate that information to the lower layers, maybe that lower layer can take advantage of the fact that some objects are not going to live long, and or they're not going to be they're not going to be touched long. So which means that you may allocate them to rows that are not going to be refreshed often, right? Or you may consciously decide not to refresh those rows those objects are allocated in, right? So now I gave you an example of breaking the abstraction layer between the language or program and the memory controller, right? And of course, this requires information communication, and you need to do this correctly so that you don't get a wrong answer in your program. But this is something that could potentially be done. And there are actually works that have explored this direction, which I can point people to in Piazza later on. But that's one example. You could do a similar thing in the operating system also, which may be easier to do, frankly, because operating system has more information in terms of allocation of memory. And you could do it in the microarchitecture, etc. Right? Okay. Basically, you could match information about which rows can retain how much data to the information of how long a piece of data needs to be stored inside the memory for. And that's a very interesting direction, I think. I would recommend thinking more potential directions like this. Now, if you're in a nice classroom setting, I would ask you more questions on ideas, but maybe we should move on. Any questions, actually? Are there any ideas? Okay, I see some people have written some things, but maybe those are old chats. Okay, yeah, those are old chats. So if you're writing something, let me know. Or if you want to speak, let me know. Otherwise, I'm going to go to the next slide. Okay, I'm going to go to the next slide. So now we're going to dig a little bit deeper, basically. So clearly, there are a lot of things that we can potentially do with this information. I'm going to give you one example of what we can potentially do. Okay, let me give you one more example of what we can potentially do. You can say, okay, this is my memory. I've determined, let's say, okay, I have to go back, this profile. And you tell memory, you tell the operating system, these are the rows, physical rows, and these are how much they can retain data. And the operating system can say, okay, this looks interesting. I don't need these rows, so I'm never going to allocate anything to them, right? Basically, I'm never going to allocate any data to a row that can retain data for less than 256 milliseconds. Because there are so few rows like that anyway. And I'm not that much memory constrained. And the operating system can tell the memory controller, I'm guaranteeing you this. Now please reduce your refresh rate to every 256 milliseconds. Now that way you're guaranteed, hopefully at the software layer, if your information is correct, that you're never going to need a refresh that's more frequently than every 256 milliseconds. So that's another powerful benefit of co-designing across the stack, as you can see. Okay, that was proposed, by the way, in a paper that we may actually look into also. Okay, so what we did actually is to understand what this profile information looks like. So you're curious about something. Can you actually refresh things less frequently? And what is the extent to which you can refresh things less frequently? So how do you figure that out? Basically, we built this infrastructure essentially for that because we thought DRAM refresh is a really important problem. We should solve it in our research because no one has really solved it. And we want to understand it. So how do we understand it? Basically, we built an FPGA-based DRAM testing infrastructure using these Xilinx boards. This is actually the earliest form of that infrastructure. It's essentially a simple memory controller. And to this board, you can attach some DRAM chips, or DIMMs actually, DRAM modules. And you can program the FPGA-based memory controller to test the different DRAM rows to figure out how long can they retain data. So you basically write some data to the row, and you read it after some milliseconds. You check if the data retention was there. Basically, you got the same data that you written. That's the idea. That's profiling, basically. You're profiling and testing DRAM, figuring out how long each row can retain data. And you basically, of course, do it with experimental rigor. You don't test everything once, right? You test everything many, many times to build a confidence in terms of what you're seeing is really correct and it's not subject to some other noise that you observe in the system. So these real system experimental studies require some rigor so that you can do them correctly. And we're going to see even more of these things that you need to check to understand, to develop rigorous experiments. So that's what we did actually. As early as 2011, actually, we started this in 2011, built these boards, and the first paper was published in 2013. I'm going to talk about some of these things later on. And this is actually the infrastructure where we did the row hammer experiments on. So And this infrastructure is actually released to the community. I don't have those slides, but it's called SoftMC. And these pictures predate SoftMC release. Okay, so basically it's a temperature controlled, and we tested a bunch of DRAM chips, and we figured out that this retention time actually holds. And I'm not going to bore you with the data. You can read the papers, which we're actually going to assign later on. But we basically verified that this retention time profile is real at high temperatures. At low temperatures, actually, you can actually increase the retention times actually increase even more. But there are always some cells at high temperatures that are very, very weak. But that's a very small fraction. So let me give you another example. This is actually data from Samsung, which we verified with our infrastructure. But this is the refresh interval. And this is the cumulative cell failure probability, as you can see. And this is the number of cells that fail in a 32 gigabyte DRAM system. So cutoff is at 64 milliseconds. So only 30 cells fail if you increase the refresh interval to 128 milliseconds in a 32 gigabyte DRAM system. 30 rows. They're randomly distributed, it turns out, on the DRAM chip. And around 1,000 cells fail if you increase the refresh interval to 256 milliseconds. So it's not that bad. But again, there are failures. So you cannot do this blindly. You need to really figure out which cells fail and make use of that information somehow. But the key observation is that overwhelming majority of DRAM rows can be refreshed much less often without losing data. And again, I'll ask the question, can we exploit this to reduce refresh operations at low cost? I've given you some ideas. And I'm going to focus on one particular idea. So I already said this, only 1,000 rows in 30 gigabyte DRAM need refresh every 256 milliseconds, but you refresh all rows every 64 milliseconds. Again, this says cells, but these cells are randomly distributed across the DRAM chip, meaning they actually map to different rows. This is actually really interesting, understanding the spatial distribution. Because process manufacturing variation is random, at least this part of manufacturing variation is random, these 1,000 cells map to different rows. Okay, the key idea that we're going to exploit is to refresh at the memory controller weak rows more frequently, all other rows less frequently. Actually, this could be implemented at the memory controller. This could also be implemented at the memory chip itself. So there could be different places where it could be implemented. But this is the idea. And this was presented even before we developed our infrastructure, because we developed the infrastructure to test whether this key idea is going to be viable and how can we make it viable. So let's talk about this a little bit. So there are three parts to this idea. You need to profile, basically. You need to accurately identify the retention time of all DRAM rows. And this is going to be the hardest step, as we will discuss, because it's really not easy to do this profiling. And we figured this out over a long course of research, where we learned a lot of things and where we educated the community about a lot of things also. This turns out it can be done at design time or during operation while the system is running. For example, you have your computer running right now. If these retention times change over time for whatever reason, the memory controller can profile the memory once in a while, intelligently, of course, without causing a lot of trouble to the system, and find out how often it needs to refresh different parts of memory, right? And if it does this nicely and accurately, it could be a win-win for everyone, right? You don't notice that this is happening in the memory controller, and memory controller is over time optimizing performance and energy. Okay. But this profiling needs to be done correctly to be able to do that. And the next step is, once we have this information, we store that information into bins based on retention time. Basically, memory controller needs to keep track of this information. If you actually expose this to the operating system needs to keep track of this information. And how do you keep track of this information becomes an issue in a scalable way, in an efficient way. So for this purpose, we use Bloom filters. Actually, let me take a vote over here. How many people know about Bloom filters? You can raise your hand, or we need to find a good way of doing this. Okay, I see raised hands. That's good. Okay, but I don't see 50 raised hands also. So not many. If you've taken my digital design and computer architecture course, then you will raise your hand, because we talked about Bloom filters a little bit over there. But if you've taken some data structure courses, Bloom filters are also a very nice approximate set membership data structures. So I'm going to talk about these, even if you don't know about them. But they're basically a way of representing set membership. Basically, that's what we're trying to do over here. Basically, we figured out the retention on different DRAM rows, and we divide them into different sets. We want to store them set by set. Okay, these are the set of rows that need to be refreshed every 64 milliseconds, and these are the set of rows that need to be refreshed every 256 milliseconds, assuming that you have two sets in this case. And you can do this efficiently by balloon filters. So let's get back to that in a little bit. I like balloon filters a lot. They're actually very nice hardware-friendly data structures, but they're not only hardware data structures, they're also software data structures. So hopefully you'll learn about them. Okay, the profiling gives you this information, and hopefully this is it. And binning, actually, if you're efficient with balloon filters, you can have very small storage overhead with binning. Okay, and the next step is refreshing. And I would argue that the binning, the novelty of the radar paper is really the binning part. It provides a mechanism for doing this very efficiently with balloon filters. And then refreshing is an easy step. Memory controller, basically, whenever it needs to refresh a row, it checks which bin the row is in. And if the row is in the 64 millisecond bin, it refreshes every 64 milliseconds. If it's in some other bin, it refreshes at the frequency that is dictated by the bin. That's the idea. So assuming that you did everything perfectly, what would you gain? Let's talk about that before going into details. So one of the beautiful things about being an architect is what you can actually check what is the benefit of a mechanism without actually going into the detailed nitty-gritty implementation details of a mechanism. You can simulate some basics and you can understand whether or not that mechanism is actually worthwhile exploring further into the nitty-gritty. That's the idea. That's why, as an architect, you never start with the nitty-gritty. You start with the big picture. Okay, refresh is a problem, and I have a solution idea. Now, first of all, let me see if the solution idea is going to provide me some reasonable benefit, assuming that I have handled profiling somehow. Right? And that's what we're going to do. So we go and simulate. We're going to talk about simulation later on in these lectures. We're going to have a simulation lecture. This is going to be a key tool for a computer architect. You simulate some workloads in a microarchitectural simulator. In some other way, you determine the hardware cost. And assuming this kind of system, the hardware cost is 2 balloon filters and 1.25 kilobytes, which is really low. You simulate and you figure out refresh reduction is 74.6%, which is quite good. Again, you simulate and you figure out that this leads to a dynamic DRAM energy reduction of 16%, which is quite good, I think. And idle DRAM power reduction is even higher because in the idle mode, you're not accessing DRAM. So a higher fraction of the power goes to refreshing because all you're doing is refreshing and leakage. And it turns out the performance improvement on the workloads we examined is about 9%. So this sounds overall really good, right? Because you're reducing energy, you're reducing power, both in idle and dynamic time, meaning while workloads are executing. And you're also improving performance on top of that. It's always a good optimization to have when you're improving both performance and energy at the same time. And at the same time, your hardware cost is not very high. And of course, we're not designing things for today. We're designing for future, right? So we also look at the scaling benefits. And benefits also increase as DRAM scales in density. So this is one example over here. This is the DRAM energy reduction at a 4 gigabit device capacity. It's 16% only, let's say, if you find that low. But if you have a 64 gigabit device, the energy reduction is actually 50%. So basically, you're halving the energy per access that you have to DRAM if you employ radar perfectly. That's the idea. That sounds good to me. So that immediately tells me that this is an idea we should investigate further and try to make it real. Okay, that's the same is true for performance improvement. So this is 4 gigabit device. Performance improvement is only 9% over here. At a 64 gigabit device, it's actually more than double. You can see it's 108%. And there are multiple reasons for this that are discussed in the paper. Because what happens is refresh becomes a much bigger bottleneck at a 64 gigabit device, and applications start delaying each other a lot. And there becomes a lot of unfairness in the system on top of that. And performance really tanks. So now this simulation is very useful to an architect and says, okay, let's investigate this further. And that's the radar paper, basically. That's the thing that started what I'm going to talk about next. The question, and this is one potential reading for your homework 1 assignment. I'd recommend reading it because you will learn about balloon filters also. And if you're interested, there's further readings that I will recommend. This is a position paper that I had written saying that we should really look into these memory scaling issues. And this is another way of solving the refresh problem just from a performance perspective by parallelizing refresh with accesses. Okay, so before I go deeper, I will show talk about this takeaway again. Basically, here we're kind of broken the abstraction layers again. We know what's underneath. At the device level, we have very varying, at the circuit level, let's say, maybe not the device level. At the circuit level, we have retention times that are quite different from each other. And if we expose them to an architectural level or memory controller, let's say, you can solve the problems, assuming that you can do the profiling perfectly. Okay, and the second takeaway is something that I've said, but I've never put down into words over here. Cooperation between multiple components and layers can enable more effective solutions to systems. And I think I've given you many, many examples of this and many, many idea directions also. So in the remaining time, let me dig deeper. So we have this nice idea. How do we make it work? We quickly realize that it doesn't work because it relies on this profiling step that we assumed. But I think we were justified in assuming that because, again, we're architects. We want to enable solutions into the future. If you actually don't show that there is benefit to a higher level idea while making an assumption, then you will never get to the implementation of the higher level idea, in my opinion. So let's make Radar work. Any questions? Okay. Okay, I saw something. Let's see in the chat. Oh, okay, this is an older chat. Okay. So let me actually, before we go into making work, I will say that good ideas are a dime a dozen. Basically, this is an American saying, which means that good ideas are everywhere. You can get a dozen of them with a dime. A dime, if you don't know it, it's basically 10 cents, 10 US cents. It's actually even less valuable right now, for good reason probably. But basically, good ideas are everywhere. And sometimes you develop good ideas, but other people also develop those good ideas. Making them work is oftentimes a real contribution, actually. And we're going to look at how to make Radar work. Maybe I'm not going to give you the exact results over here, but hopefully give you a thought process. So Radar's mechanism was like this: profiling, binning, and refreshing. So at the time we wrote the paper, we said that profiling is easy. And at the high level, profiling is actually very easy. What do? Somebody needs to do this, basically. You write data into a row, you prevent it from being refreshed, and you measure the time before data corruption. And of course, this is not easy to do, right? You need to basically do multiple rounds of testing. So let's assume that you wrote once to all of the rows. We wait for 64 milliseconds without refreshing. And at the end of 64 milliseconds, you look at the rows, and everybody still has once. Okay. Now, you cannot wait. Clearly, these rows can contain data for 64 milliseconds. And then you look at this after 128 milliseconds, and you see that one of the rows has a corruption, but the other rows are intact. This means that this row cannot detain data for less than 128 milliseconds, right? You figure this out. That sounds good. But this doesn't mean that the other two rows can retain data because you haven't done enough testing. That's one reason. Second reason, you start out with this data pattern. What if you had some other data pattern, right? And we're going to talk about that. That's an issue. So you need to do enough testing, and you need to actually cover the worst case. Have we covered the worst case? Of course, you can do this profiling at different temperatures and have different profiles at different temperatures, and the paper talks about that. So we're assuming we're doing profiling in a single temperature, and we're using that for that temperature range during operation. Okay, another row doesn't retain data after 256 milliseconds, so you mark that as 256 milliseconds. But again, you need to do enough testing to ensure that you're not making a mistake. Okay, that's why profiling is not easy. You need to do enough testing. You need to exacerbate the worst case. And I haven't shown you the even worse problem that we will get to in a little bit. Okay, so is this really this easy? Not really, as I said. So there are two major challenges to DRAM retention time profiling, which we will talk about. One is data pattern dependence, as I already alluded to, and the second is variable retention time. So let's talk about that. So what is data pattern dependence? It's actually very simple. It's the idea that retention time of a DRAM cell depends on its value and the value of the cells that are nearby it. And this is very fundamental. All memories have this sort of data pattern dependence issues. And why is it fundamental? Because there's interference or coupling that happens between different cells. Okay, so let's go into a little bit deeper. when a row is activated, all of the bit lines are perturbed simultaneously. So I'm showing you a row of 3 cells, and there are 2 rows over here, and there are in between rows over here. These are the word lines, these are the bit lines. When you activate this row, let's say, all of the bit lines, the vertical bit lines, are perturbed simultaneously. Because what happens when you activate the row, access transistors get connected, capacitors leak charge, and they basically perturb the bit lines. Now you need to sense those bit lines. And this perturbation causes electrical noise on the bit line. And that electrical noise actually affects the reliable sensing of this DRAM cell itself. And the magnitude of that noise is affected by the values of the nearby cells. So basically, nearby cells affect this cell. So why? Because you have bitline to bitline coupling. There's electrical coupling between adjacent bit lines over here. The value in these cells affects what's happening in this cell. There's also bitline to word line coupling. There's electrical coupling between each bit line and the activated word line. Basically this and this. You can see the blue one and the red one over here. And that affects the value of this cell in the end. Which means that even when you're not accessing, actually, you're hurting the value of this cell because you actually have this sort of coupling. Okay, so this means that retention time of a cell depends on data patterns stored in nearby cells. So if the data pattern is 1, 1, 1, your retention time may be better compared to if your data pattern is 1, 0, 1. Because this coupling actually becomes worse depending on the voltage differential between the bit lines and the word line. If the voltage differential becomes higher, then the coupling becomes higher also because there's much more tension. And as a result, and your electric fields are much stronger, of course. And as a result, your coupling is stronger. So you need to find the worst data pattern to find the worst case retention time. And it turns out this is not easy. So let's talk about the implication of this data pattern dependence on profiling mechanisms. So any retention time profiling mechanism must handle data pattern dependence of retention time. The intuitive approach is to identify the data pattern that induces the worst case retention time for a particular cell or device, right? But there's a problem. It's very hard to know at the memory controller which bits actually interfere with each other due to, because the memory controller doesn't know which cells are actually close to each other in DRAM. Because there's an opaque mapping of addresses to physical DRAM geometry. So why? We'll see this later on also. Logically consecutive bits from the memory controller's perspective. So a memory controller has, for example, row 0, row 1, row 2, row 3, row 4, row 5, row 6, row 7, right? These are logical addresses from the memory controller perspective. Those logically consecutive rows from the memory controller's perspective may not be physically consecutive. Similarly, logically consecutive columns may not be physically consecutive either. And this is because internally, DRAM manufacturers do remapping of rows and remapping of columns. And this is because they need to handle reliability. So let's assume that you're the DRAM manufacturer. You manufacture the DRAM chip. Row 5, it turns out it's faulty. Some of the values are stuck at 1. What do? Throw away the DRAM chip? No, you don't throw away the DRAM chip because it's very costly. What you do is internally rewire row 5's address to some other row, some spare row in the same subarray, in the same bank, let's say. We haven't talked about subarrays. But in the same bank, such that whenever you need to access row 5, it goes to some other row, some other spare row that you actually put in to the DRAM chip to handle such faults. So basically, these are redundant rows, and there's some internal remapping that happens to ensure that that's not exposed to the memory controller, that's not exposed to anywhere else in the system. And this sort of not exposed mechanisms actually makes life harder on the memory controller side, on the operating system side, because these parts have no idea about the physical mapping of rows, for example. So basically now you cannot say this row is adjacent to this other row from the memory controller level. Right? That's the idea. And also there are also interesting second order bitline coupling effects that are really hard to figure out, in my opinion, as the circuits become smaller and smaller. I call these quantum-like effects, actually. And DRAM is a circuitry that's actually at a very small nanometers today. It's actually much worse than logic, in my opinion, because cells are much smaller than logic today. So there are some coupling effects that happen between the bit lines and the word lines that are very non-obvious. It's very hard to model also at the circuit level. So it becomes very difficult to actually determine the data pattern dependence. Now the DRAM manufacturer can determine it much better, of course, But even they have difficulties in terms of worst data patterns. But there are ways actually to do the testing, and the paper that I mentioned actually does a lot of testing that I'm going to very briefly talk about. We may get into it later, but this is not easy. Okay, any questions? Okay, but we're going to assume that you can do this, and actually there are mechanisms that are developed to do test DRAM to take into account this data pattern dependence. What becomes worse is what I'm going to describe next. It's called variable retention time. It's actually a very, very interesting phenomenon. Again, it's another quantum-like phenomenon in circuits. In circuits, basically. And the idea is this, basically. It's very simple. Retention time of a DRAM cell changes randomly over time. This means that you test the DRAM cell at this point. It can retain data for 10 seconds, let's say, strong. You test the DRAM cell, I don't know, a day later, and it doesn't retain data for even 8 milliseconds. This sounds very sad, right? But it does happen, actually, and we've seen it in our experiments. And it was discovered in late 1980s by Yeni. It's a very fundamental problem. It exists in other circuits also, but DRAM has approached the scaling limits a lot, that we're seeing a lot more of this today. Basically, a cell alternates between multiple retention time states. And why does this happen? Okay, I'm going to dig a little bit deeper, even though you don't really need to know why does this happen deeper, but I think understanding these processes underneath sometimes is very nice. So what happens is the leakage current of a cell changes sporadically because charge gets trapped in the gate oxide of this DRAM cell access transistor. And this trap of the charge happens randomly. Okay, when the trap becomes occupied, charge leaks more readily from the transistor's drain, leading to a very short retention time. And it turns out, well, this is called trap-assisted gate-induced drain leakage, TAGIDL. And it appears to be a random process. Other folks had shown this, and we've actually shown it again, that it's a random process. And this, basically, worst-case retention time now depends on a random process. Then the question is, how do you figure out the worst-case retention time of a cell? If you would like to refresh the cell at the retention time it needs to be refreshed at. Okay, this is a good question. But this question doesn't concern only Radar, right? This question actually concerns DRAM manufacturers. Now, the DRAM manufacturer needs to guarantee that the DRAM chip needs to work, let's assume, at some refresh rate, 64 milliseconds. Today it's 32 milliseconds. This is one of the reasons why it's becoming 32 milliseconds, by the way. They cannot guarantee it at higher refresh latencies, but they claim that they can guarantee it at lower refresh rates. So basically, it becomes difficult because you need to test DRAM for much longer to see the worst case retention time. And in our work, we figured out that you need to test DRAM for days and days and days, actually, to figure out the worst case. And even after that, you cannot be sure that you've actually covered the worst case for all cells because of this random process. So it may actually take much, much longer, weeks, months, to figure out the weakest cells to transition into this worst case retention time states because of this random process. And if you think about it a little bit, and if you blink your eye, this is kind of like quantum, right? In a sense, this should not be random, right? Whenever you test something, you should get a predictable answer. But we're not getting a predictable answer. We're getting a random answer in terms of retention times right now. And it's a quantum-like process, basically. So you need to find the worst case despite this random process. And this makes things much harder. And this is one of the reasons why I believe more errors are slipping into the field, because it's a very tough problem for the DRAM manufacturer also. Now let me give you another tidbit, even though we're running awfully late on time. You can say, okay, this problem is DRAM manufacturer's problem, and they should figure out a way to solve it. You're partially right, but if you actually take a DRAM chip and solder it on a board or in a DIMM or a module, let's say, you're actually messing with the retention times. Why? When you're doing soldering, you're actually exposing at least parts of a DRAM chip to high temperatures. And those high temperatures actually change the DRAM retention time of different cells. And that doesn't sound very good. Now, actually, manufacturer may tell you, okay, I guarantee you operation, but now you're taking the DRAM chip and you're exposing it to very high temperatures. You're doing something that DRAM manufacturer couldn't test, and you're changing the retention time, so all of the profiles can change to some extent. And as a result, a good place to do this sort of profiling is actually the system, in my opinion. In the memory controller, if you have an intelligent memory controller, you can keep profiling the retention times. Okay, so basically, you can. It's hard to blame the DRAM manufacturers on this one because the DRAM chips are not are actually subjected to some extra things later on, like soldering. Okay, so this is a real example of a VRT cell. You're looking at a real example plot from one of our real chips. We've tested the chip for hours, as you can see. And this is the retention time. This is at very low temperatures. I believe it's at 45 degrees Celsius. That's why the retention time is very high for that particular cell. And we didn't test beyond 6.1 nanoseconds. Basically, that was the longest we tested. Assume that that's the longest. But you can see that the cell alternates. The retention time is not constant, right? It's alternating between multiple different states. And the lowest state is over here, as you can see, 2 point something seconds. Okay? So that's interesting. So at high temperatures, actually, there's a temperature dependence. As I said, at high temperatures, circuits become more leaky. And we've shown in our paper that every 10 degrees Celsius, as you increase the temperature by 10 degrees Celsius, you reduce the retention time by 46.5%. And this is very predictable. You can look at our paper. There are curves from real devices that show that that's real, which means that the temperature actually reduces the retention time exponentially. Right? At 85 degrees Celsius, all of these seconds become milliseconds, hundreds of milliseconds. Now, if you want to go to 100 degrees Celsius, junction temperatures, operating temperatures, that becomes even lower, right? Okay, so you got to be careful about temperature, clearly. Okay, so if you're interested in how to do these experiments, we have a sophisticated methodology, clearly. We want the temperature to be constant, for example, and you can read the paper. And we have a lot of interesting projects related to this, if this is something that attracts your attention. So this is another plot from a real chip that basically shows the variable retention time phenomenon. So what am I plotting over here? On the x-axis, there's a minimum retention time in seconds. On the y-axis, that's the maximum retention time in seconds. And we're plotting every single cell. So basically, every single point corresponds to every single cell. Of course, there are too many cells to have a point for. So really, this is a density distribution. So you can see that the darker parts have many, many more cells. The lighter parts have fewer cells, but there are some cells. The parts that are white don't have any cells in that x, y point. Okay? So since a DRAM chip has many, many cells, clearly we need a density distribution. So, okay, for the first thing you would expect, if variable retention time did not exist, you would expect everything to fall into the x equal y curve, right? Nothing should really deviate from it. A cell's retention time should be the same as what you tested before and the same as what you're going to see later. But that clearly doesn't happen. There's clearly a lot of variable retention time that's happening across cells. And this is true for this manufacturer, but that's true for all manufacturers that we've tested. And it turns out most failing cells actually exhibit variable retention time in our experiments. And many failing cells actually jump from very high retention time to very low. You can see that at some point your retention time is 1 second. At some point later, it's 6.1 seconds. By the way, we tested at most up to 6.1 seconds. These actually the cells actually can contain much longer data over here. Okay. Let me continue. If there are questions, please interrupt me. So let me finish the implication of retention time profiling mechanism, and then I will take a look at if there are questions. But basically, we have a big problem. There does not seem to be a way of determining if a cell exhibits variable retention time without actually observing a cell exhibiting variable retention time. And we have tried hard so far to model this, but because it's a random process, it's very hard to model it. It's a memoryless random process. So VRT complicates retention time profiling by DRAM manufacturers because later you expose the DRAM to high temperatures and you can induce VRT in cells that were not previously susceptible. I said that given the example of soldering, right? And as a result, manufacturers' retention time profile may not be accurate. So basically, in the paper, we concluded that one option for future work is really to include error correcting codes inside the DRAM chip and to continuously profile DRAM online while aggressively reducing the refresh rate. So this is a mouthful. What does this mean, basically? This means that you reduce the refresh rate a little bit, and you have error correcting codes, and you get feedback from the error correcting codes. Basically, if you reduce the refresh rate too much, and if a cell failed, that means that error correcting code says, oh, you actually reduce the refresh rate too much, so back off for that growth. So if you have error correcting codes, you can play nice tricks like this. Basically, you can have a back off mechanism, hopefully without getting data retention errors, because error correcting codes are actually correcting the errors that you have caused because you reduced the refresh rate for a single row. That way, you can continuously change the refresh rates for different rows and get feedback from the error correcting codes and figure out that you've done something wrong if you actually have error corrections that are happening. But if you don't have error corrections happening, you can reduce the refresh rate aggressively for rows that do not require more refresh, frequent refresh. That's the idea. And this was the option that we proposed for future work. And we actually have other future work that I'm not going to talk about at this point, at least, that provide this. But DRAM manufacturers actually took up on the idea, and they actually implement error correcting codes today. If you look, but unfortunately not in the way that is nice, in my opinion. So because this variable retention time is a huge problem for DRAM manufacturers, what they did was they added error correcting codes inside a DRAM chip, and those error correcting codes automatically correct errors that happen inside DRAM. Unfortunately, this is completely transparent to the memory controller and the system. So a correction may happen, and that correction doesn't get exposed to anyone else in the system. DRAM manufacturers have secrecy reasons why this is the case. But because this is not exposed to the system, this actually complicates life in the memory controller if you want to build a mechanism like Radar. And maybe we'll get back to this later on. We actually do a lot of research to understand this. But basically, and this is a very fundamental problem. It's a research problem in DRAM, but in flash memory, for example, there are a lot of error correcting codes that happen and things get corrected at the flash memory controller. I will actually talk about that very briefly if we have time later on. But this is another example of you need to cooperate between the memory controller and DRAM. You should not really do things that are not transparent. And we may talk about that later on when we get to it. Okay, but of course, when you add error correcting codes, you need to keep error correcting code overhead in check, because if you add too large error correcting codes or too strong error correcting codes, now you may actually be spending a lot of storage, density, and also energy on error correcting codes itself, right? On correction itself. That doesn't sound good also. Okay, so this is basically the paper that I've mentioned that looks at experimental study of data retention behavior. And I recommend reading that. This may be one of the papers that we actually assign as part of the readings. But this is actually the next paper that came out after Radar that started a lot of research on how to actually profile for DRAM errors. So let me actually look at it, and there's a question basically. Okay, yes, I think somebody asked a question. Can you actually, since you have a relatively low amount of slow cells, can't you just ignore those and globally refresh slower and then let error correction take care of it? Or maybe add some more redundancy that would allow this. And this is actually along the lines of what I've discussed earlier. Yes, you can ignore a lot of those cells, but you need to do something with those cells. Maybe, yes, you actually add error correction just to those cells. I think those sort of ideas are good, but you need to keep error correction overhead in check. So that's another, once you know the retention time profile, that's another thing that you can consider. So I like those ideas. But all of those require you to know the retention time of cells accurately. If you make a mistake, even if you corrected the error correcting codes, you may not be perfect, because you need to know how much error correcting codes you need to protect things with, right? Okay, so let me continue a little bit. But it's good that you guys are proposing ideas. I like this actually. And let's actually continue this on Piazza also. Okay, I'm a little bit awfully behind, but I'm going to continue. And I think what we're going to do with course logistics is I'm going to record something, and if there are questions, we'll handle them over Piazza, since it's not going to be a surprise to anyone. Course logistics are very similar to last year, and grading is on the catalog anyway. Okay, so let's talk about how can we reliably find the retention time of all DRAM cells. It's a fascinating problem. Our goal is so that we can make DRAM reliable and secure, because this is a problem that DRAM manufacturers face anyway. Even if you don't want to employ something like Radar, you need to figure out the retention time of DRAM cell so that you can say the refresh rate that I'm going to pick for the system is correct. It's going to guarantee correctness. And at this point, we don't even know actually, frankly, the answer. That's a bit sad. So there may be some retention failures that are slipping into the field, in my opinion. Okay, and also make techniques like Radar work. So if you want to be even more aggressive, you still need this profile information to improve performance and energy. So we've done a lot of work in this area. So this is our next paper. I'm going to briefly give you some ideas. I'm not going to go into detail, and then this is our next paper, one of the next papers that takes into account variable retention time and handling data-dependent failures, and handling data-dependent failures even more, because there are many solutions that you can explore. And I think these are all good solutions. And this is one of the latest works that is from one of the TAs, actually, Minesh and Jeremy, actually both of the TAs. This is actually really interesting because it was the first analysis of the low-power chips and their retention time profiles. It basically showed that the problem is getting worse and worse over time. And it provides a fast and robust profiling mechanism at higher refresh intervals and temperatures. Basically, if you want to find a good refresh interval and find the failing cells at a refresh interval X and temperature Y, increase the refresh interval and increase the temperature, increase the refresh interval, increase the temperature, and test at that point. This gives you a superset of failing cells at the refresh interval you're targeting. That's why it's called reach profiling. You're reaching to some other refresh interval that's more aggressive, some other temperature that's more aggressive, to find the superset of cells that would fail. And this is actually much more robust than previous retention time profiling mechanisms. And this also goes into the complex trade-off space of retention time profiling, which we may talk about later on. So this is actually really interesting, I think. And of course, as I mentioned, manufacturers started adding ECC into DRAM, and they decided to not expose this information to anyone. As a result, this complicates things, because now we want to do retention time profiling in the memory controller, but you don't know what's being corrected and what's not being corrected. And on top of that, once you add ECC, and this is very fundamental also, you add error correction code into a system, it corrects errors. There will be some errors that it cannot correct. In this case, for example, it's a single error correcting code. If there's a single error, meaning there's a single error at the granularity you're doing the correction, you can correct that bit. Now, what happens if there are double errors? If there are 2 errors at the granularity, you cannot correct that bit. What happens if there are 3 errors? You cannot correct that bit. Now this gets exposed to the memory controller as different types of errors, because while you're correcting, you change the data, and now the memory controller may make no sense of what's happening, because you introduce new errors into the system while you're correcting them. And this paper shows that you introduce those new errors into the system, but you can mitigate that by doing some reverse engineering. And this most recent paper that's going to appear very soon at Micro actually shows that you can actually reverse engineer the complete error correcting code function that DRAM manufacturers were trying to hide in the first place by being intelligent about your profiling. And that's the idea. Okay, so we're going to get back to it. So actually, reverse engineering error correcting code functions is really interesting. First of all, you want to enable techniques while somebody's not cooperating, in this case, DRAM manufacturers. That's good. That's one good reason for reverse engineering. The other reason is actually to find out the vulnerabilities in the system, because error correcting codes have been posed as protecting for rowhammer, for example, by the DRAM manufacturers, but they're actually not very good at protecting against rowhammer, and reverse engineering them and understanding them actually are very beneficial. Okay, so let me go into the binning. I'm going to talk about Bloom filters relatively quickly. Now we're assuming that you could do this profiling with lots of research. How do you efficiently and scalably store rows into retention time bins? And the idea is hardware Bloom filters here. So some of you mentioned that you know Bloom filters, some of you didn't. That's okay. I'm going to go over the high-level idea here. Basically, this is a beautiful probabilistic data structure that can compactly represent set membership, or presence or absence of element in a set. And it's non-approximate. Basically, it's approximate. So what does it mean? A non-approximate set membership is you use 1 bit per element to indicate the absence of presence of each element from an element space of n elements, right? Okay, this is very theoretical maybe. Approximate set membership says, I want to use a much smaller number of bits and indicate each element's presence or absence with a subset of those bits. Some elements map to the bits other elements also map to, which leads to false positives. So in this case, we want to have operations insert, test, and remove all elements from this Bloom filter. So let me give you an example of a Bloom filter. Actually, here I think I'm going to test whether I can share from my iPad because I want to give you an example by writing. And this is a good test for future lectures also, I think, if I can log into my iPad. Unfortunately, there's also that we need to deal with. So let's see. The host should let me in. I guess I can let myself in, but okay. So I don't need call. Okay, wait a second. I don't want that. Okay, I'm going to leave this. So sorry. Whenever I connect, I should not connect with the sound on. Okay, cancel. That's good. So this doesn't have sound on. Let's see if I can share. Only the host can share. Can you make me the host, the new person who is connected? I guess someone can make me the host, hopefully. Okay, I'm the host now. Okay, I guess maybe let me stop sharing over here. Wait a second. Okay, I'm still not the host. You need to make the right owner mutlu host. Okay, let's see. More. Make co-host. Okay. Okay, that's good. Now I can share content. Whiteboard. Okay, can you see my screen? That's good. So basically, what we're really trying to do is, okay, I don't want to see myself on the screen. What we're really trying to do is, so we have retention time bins, right? So everything that needs to be refreshed every 64 milliseconds. And everything that needs to be refreshed every 256 milliseconds. And we have a set of rows for this, right? Let's say row 1, row, I don't know, 50, row 5,000, dot, right? Okay, maybe we have only 50 rows here. It doesn't matter actually how many rows you have. And then you have rows that need to be refreshed every 256 milliseconds and every 256 milliseconds. And this is a bigger set, right, clearly. And this is an even bigger set over here, right? Every 512 milliseconds. Actually, you don't need this, right? Because everything else that doesn't fall into these sets, you can assume that you need to refresh them every 512 milliseconds. So, okay, you don't need this, keep track of this. But you do need to keep track of the set of rows you need to refresh every 64 milliseconds and every 256 milliseconds. Okay, one way of doing this is clearly a list of rows, right? Now, that doesn't sound very good because you need to actually have all of the list of rows and communicate them. That doesn't sound great. And actually, if you increase the size of memory, you need to actually increase the size of that linked list. It doesn't need to be a linked list, but it could be a table, right? You could actually list the row addresses. That's one way of doing it. I don't think that's really a great idea, but there could be ways of doing it. We're going into implementation now. Another way of doing this is have a single bit vector. Okay, this is my bit vector. Okay, this is my entire memory. However many rows I have, 2 to the 40 rows. I just made it up. And I have 1 bit for each row. 1 bit for each row. 1 bit per row. In this case, I'm going to basically set that bit for every row that requires refresh every 64 milliseconds, right? So there will be only 50 rows with that bit set, even though I have 240 rows. So this is inefficient, but it's exact representation. And I'm going to have another bit vector over here for, again, 200 to the 40 rows, because that happens to be my memory size, and 1 bit per row. And I'm going to set the bits for rows that require refresh every 256 milliseconds over here. So basically, this is the bit vector for every 64 milliseconds. This is the bit vector for every 256 milliseconds. They're of the same size. They're both to the 40 entries. They're exact. They're not approximate, and this has more entries clearly set to 1. So the overhead of this is clearly not that great, right? I don't want this sort of overhead. It's 2 times 2 to the 40 bits. Now, balloon filters allow you to reduce the size while losing some accuracy. Basically, I say, okay, 64 milliseconds. I'm going to represent the rows that fall into this bin using a much smaller balloon filter. I don't know, let's say 10 entries, 10 bits. That's much better than 2 to the 40 bits. And I'm going to insert the rows into the balloon filter. Basically, every row that I'm going to represent with some number of bits over here, let's say 1 bit initially. And I'm going to take each row that needs to be in this filter and go through a hash function to decide which bit to set. And okay, I insert row 1 to this location because hash function tells me that whenever I need to access balloon filter, I go through this hash function so that I can distribute the bits relatively equally in this Bloom filter. So I basically populate this Bloom filter with the list of rows or addresses of rows that need to be refreshed every 64 milliseconds, right? So you have, essentially, if you have 50 over here, we'll have maybe 50 over here. So 10 entries may not be a good idea. Let's assume that you have 100 entries over here, right? Okay, you determine the size of the Bloom filter such that not everything is a 1 over here. That doesn't sound very good. It could be also 1,000 over here. Okay, so basically you insert bits such that some of them may map to the same location over here, but everything is inserted. But now your representation is much more compact. And you do the same thing. Let me use a different color over here. Basically have a larger Bloom filter, let's say 10K bits, and insert into that Bloom filter the rows that essentially need to be refreshed every 250 milliseconds, right? You basically take everything over here one by one and set the right bits over here. And in the end, you have a Bloom filter that has the right bits set that are associated with the row addresses that need to be refreshed every 250 milliseconds. Again, you have to go through a hash function. I didn't depict it over here, but those hash functions are important to have so that you can distribute the bits randomly. So that's the idea. So now you have a much more compact data structure, as you can see over here. This is a very compact data structure, but it's not. It's approximate. This is the result of the profiling. The profiling fills these bins in the data structures, and then the memory controller asks the question, oh, I have this row address I want to refresh. How often should I refresh it? Basically, the memory controller goes through the hash function for the row address, checks this bin. If its bits are set to 1, it refreshes every 64 milliseconds. If its bits are not set to 1 over here, then it says, I'm not going to refresh every 64 milliseconds. Then it goes to the next Bloom filter, checks if the bits for this row is set to 1, going through the hash function for that Bloom filter. And if it's set to 1, then it refreshes every 250 milliseconds. If not, it basically waits until it's refreshed every 12 milliseconds. And that's the idea. This way you can get a very, very compact data structure. And you don't really need to be completely accurate. Because in the worst case, you're going to refresh something more often than needed and never less often than needed because you've always inserted the rows accurately into the appropriate Bloom filters because your profiling is correct. Okay. So that's the idea of Bloom filters pictorially. So let me go over a little bit. I'm going to actually keep you for longer. In the future, I'm going to keep you less, hopefully. But let me finish this. My iPad is not cooperating with me nicely. I'm going to stop share over here. What I'm going to do is I'm going to share over here, share screen again. And not my desktop, but I'm going to go through the PowerPoint again. Okay. So basically, I've given you that example. So assume that this is the 64 milliseconds bin. If you want to insert a row, you need to go through hash functions and set the bits associated with that row through those hash functions. So why do you go through 3 hash functions? This reduces the probability of collisions. That's why we want to go through multiple hash functions over here. So row 1 goes through 1 hash function, which leads to this bit. And the second hash function leads to this bit. The third hash function leads to this bit. So the fact that you've actually inserted this row is being represented by the fact that these 3 bits are set to 1. That's the idea of the Bloom filter. It's beautiful because you don't need to have a bit per row. And also you don't need to have the row address inside. The representation is converted into this process of going through the hash function and setting the appropriate bits based on the row address. Okay, now let's go to the next. Now, how do you check presence of a row? And the memory controller needs to check the presence. It basically goes through the hash functions again. With the address of the row. Let's say the row address is 1. It basically checks the row addresses over here. And you can see that all 3 bits are set. And the memory controller ends the bits. Basically, all of the 3 bits need to be set for row arm to be declared to be present in the Bloom filter. And in this case, all 3 are set. And the memory controller says row 1 is present. It needs to be refreshed every 64 milliseconds. So that sounds beautiful. Now let's go into another insert. Let's check if row 2 is present. Row 2 is present. You go through the hash function through the row 2's address 2, and it maps to these bits. And you can see that it maps to 1 bit that row 1 also mapped to, but it doesn't. The other bits that it maps to are 0, and as a result, Bloom filter correctly says row 2 is not inserted. So you should not refresh row 2 every 64 milliseconds. That sounds good, right? Because this is correct. Okay. Let's assume that we've inserted row 4. The way you insert row 4 is very similar to you inserted row 1. You basically set the bits associated with row 4 through the hash functions, and you can see that they happen to map to different bits over here. Okay, so you populate more bits. And let's assume after that you check whether row 5 is present in the Bloom filter through the memory controller. Okay, you go through the hash functions again. To your surprise, we've never inserted row 5. We don't know, of course, at the memory controller, but in this case, we know exactly what we've inserted. So to our surprise right now, row 5's hash function 1 maps to here, 1. Row 5's hash function 2 maps to here, and hash function 3 maps to here. So you can see that they're all 1s, which means that the Bloom filter tells us row 5 is present even though we never inserted row 5. This is a false positive, right? Let's go back. Okay. Let's go back basically. These bits were set by row 4 and row 1 together. But unfortunately, row 5 was never inserted, but we have a false positive. As a result, unfortunately, the Bloom filter says we should refresh row 5 every 64 milliseconds. But this is not bad because we refresh row 5 more frequently. Okay, it's bad in terms of energy, but it's not bad in terms of correctness. So we don't lose correctness because we always insert a row that we know should be inserted at the correct bin. But we sometimes get these false positives because Bloom filters are not perfect. Basically, they're approximate. They basically overestimate set membership because they don't have enough bits to represent all addresses that are inserted into them. So if you can tolerate these false positives and not have correctness issues, Bloom filters are a great data structure for your problem. And Bloom filters were introduced in 1970, as you can see by this beautiful paper. And I would recommend reading this paper. Basically, it's a beautiful paper. I'll let you go through this quickly. If you have to drop off, please drop off. But I think Bloom filters are really nice. I would recommend watching it later on. Basically, this paper proposes a higher level mechanism. It's not hardware. It's not software. It's really a way of encoding things. Basically, they look at computational factors in hash coding. And they basically say they want to test a series of messages one by one for membership in a given set of messages. So you can think of this as row addresses generated by a memory controller. 2 new hash coding methods are examined and compared with a particular conventional hash coding method. The computational factors considered are the size of the hash area, which is the space dedicated to the Bloom filters, the time required to identify a message as a non-member of the given set, reject time, which is really the query time, latency of accessing the Bloom filters, and an allowable error frequency. What should be your false positive rate? And you can see that in such applications, it's envisaged that overall performance could be improved by using a smaller core resident hash area in conjunction with the new methods, and when necessary by using some secondary and perhaps time-consuming test to catch the small fraction of errors, false positives, associated with the new methods. So this is actually a beautiful paper. I recommend reading it. But let's go into, in the spirit of this course, everything is about advanced and disadvantaged. And Bloom filters, even though they were proposed as a software data structure, they're actually very good to examine advantages and disadvantages of as an architect. So this enables storage efficient representation of set memberships. That's a big advantage. Insertion and testing for set membership are actually very fast. Presence detection is really fast. And it has no false negatives. Basically, if a Bloom filter says an element is not present in the set, the element must not have been inserted. So this is a guarantee. Assuming your hashing is deterministic, which it is, and assuming you're inserting everything you're supposed to be inserting, you get no false negatives. Okay? That's beautiful. And this enables trade-offs between time, storage efficiency, and false positive rate via sizing and hashing functions. So there are 2 levers here. You can size the Bloom filters and you can change the hashing functions. Both of them clearly have effect on all these 3 things: time, storage efficiency, and false positive rate. Now, of course, it has disadvantages, false positives. An element may be deemed to be present in the set by the Bloom filter, but it may never have been inserted. Now, if your application cannot tolerate these, don't use Bloom filters. If your application can tolerate these, like in our case with the refresh, you can use the Bloom filters. Okay, that's the idea. Okay, let's talk about benefits of Bloom filters at refresh rate bins. So false positives, a row may be declared present in the Bloom filter even if it was never inserted. That's not a problem. You can refresh some rows more frequently than needed. You will eat away from some of the benefits of Radar, but you will not be incorrect. So no false negative is good because rows are never refreshed less frequently than needed. There are no correctness problems. This is scalable, so this is some benefit. we have not fully discussed yet. A Bloom filter never overflows. In the worst case, all of the bits become 1, which means that you refresh everything at the rate that's dictated by that bin. That doesn't sound good, but you don't have correctness problem and you don't have overflow problems. But if you have a fixed size table, let's assume that you size the table for some memory size, 4 gigabytes memory. Let's assume you have some number of entries. Okay, you decided your memory controller has that number of entries. Now you want to change your memory size. You make it 32 gigabytes. Now you need to increase the size of your table. How do you increase the size of your table? You cannot. You're stuck. Now you can over-provision the size of your table to begin with for the worst case memory size that you're going to ever need. Now that's not good because your table size is huge to begin with, even though you may not need it. So basically a fixed size table is not scalable. But a Bloom filter, by adding approximation to its set membership determination mechanism, becomes much more scalable than a fixed size table. And that's one of the reasons why we picked Bloom filters inside the memory controller in this case also. And also it's efficient. There's no need to store the information on a per row basis. It's simple hardware. As you can see the paper actually analyzed a lot of Bloom filter configurations, and we decided a 1.25 kilobyte configuration with 2 filters for a 32 gigabyte DRAM system is actually very nice. Okay, so use of Bloom filters in hardware is actually very nice. This is just one example, and I think you can use Bloom filters in many places in software. There are many places where they're used where you want to quickly test for something, when you can tolerate false positives and set membership tests. So Radar is one example, but I would also recommend this one. If you actually cover advanced caching, this is actually a really nice way of using Bloom filters. It basically uses Bloom filters to store evicted addresses from the filter, and actually it enables much better cache management that way. Okay, now that we've done binning in a nice way, in a hopefully elegant way, refreshing is actually easy. Basically, the memory controller periodically chooses a candidate row to refresh. It determines which bin the row is in, and it determines if refreshing is needed at that point in time. And there's an algorithm for this, but you can read the paper for more detail. This is really the easy part, refreshing. Okay, let me talk about where you could actually add Radar into. I know we're out of time, but I think it's better to finish if people are still hanging out. Looks like most of you are still hanging out, and all of this is online anyway. If you're not hanging out, I'd recommend watching it. So this is an idea, again, that could be implemented in multiple places, the memory controller or DRAM. In today's DRAM, refresh controller is in DRAM itself, auto refresh systems. They're called auto refresh systems. Basically, memory controller once in a while send a refresh command to DRAM, and the DRAM itself magically refreshes some rows that memory controller has no idea about. Now, this is going to change, in my opinion, in the future, but let's not talk about that right now. Radar can be implemented whenever you design an idea. Whenever you have an idea, you should think about different implementations of the idea. You could do it inside the controller or inside the DRAM. Let's take a look at how it's done in the controller. Basically, this is option 1. You basically have the Bloom filters inside the controller, and overhead is relatively small, as you can see. And you need to have additional commands issued per row refresh in this case. Basically, now the memory controller takes over the control. The DRAM doesn't do refresh. Memory controller basically sends activate and pre-charges to those rows that require refresh whenever they require refresh. Okay? But there are multiple ways of doing it also that I'm not going to go into. That goes too much into implementation detail, I think, at this point. Okay, the other option is also interesting. The DRAM chip implements Radar itself. So you have some logic inside the DRAM chip that implements Radar. In this case, the overhead is even lower, actually, I believe. You can see the overhead over here. But the benefits are very similar also. This way, you absolve the memory controller from issuing the refreshes at the right time, and maybe you can be more contained. But of course, the overhead is, it's easier to add logic into a memory controller compared to adding DRAM, because as we discussed, DRAM process is optimized for DRAM capacitors as opposed to SRAM logic. Okay, I've already given you, assuming you do all of this, you get significant benefits. Okay, let me cover this also very quickly because I think this will be useful for brainstorming in Piazza, for example. So what else can you do to reduce the impact of refresh? I'm not going to give you any answers. What else can you do if you know the retention time of rows? I think some of you actually already volunteered some good ideas that I would suggest you think about it more deeply also. Because this is really state-of-the-art in DRAM. You can actually push the state-of-the-art, and people are actually willing to listen in this area. How can you accurately measure the retention time of DRAM rows? I think this is going to be more and more interesting into the future. We have good mechanisms, but it's always good to have lower and lower overheads to accurately measure. Because you can imagine, actually, if you have very low overhead measurement of retention times, you can be very aggressive in the design of your system. You start with very high refresh rates and very high density chips, let's say, and over time you can make them much faster and scalable. So let me summarize. DRAM retention, DRAM refresh is actually a critical challenge in scaling memory technology efficiently to higher capacities. And there are several promising solution directions we've talked about. Eliminating unnecessary refreshes, reducing the refresh rate with online profiling and detecting, correcting any errors. We briefly talked about that. That's a very viable solution, actually. And we didn't talk about parallelizing refreshes with accesses, but I pointed you to a paper about that. And we examined properties of retention time behavior that are actually fascinating, I think. And we discussed how to enable realistic variable retention time aware refresh techniques very briefly. And I think there are many avenues for overcoming DRAM refresh challenges going into the future. How do you handle data pattern dependence, variable retention time? How do you enable online retention time profiling and error mitigation? And how do you exploit application behavior? This is actually very fascinating. I think there is more at the higher level. As I mentioned yesterday, there's plenty of room at the top. There's plenty of room at the bottom. But even more if you communicate between the top and the bottom. And I'm giving you one example, I think, here. There's plenty of room at the bottom because if you figure out these retention times, you can exploit them. There's plenty of room at the top because if you figure out how much retention you really need, you can actually exploit it. But if you communicate both of that information between the top and the bottom, you can actually enable some mechanisms that can do even better than what we discussed. And I think we've discussed some ideas, albeit briefly, but exploiting application behavior, application operating system behavior, workload behavior in conjunction with underlying device and circuit behavior is really, really important, I think. So we've cut across the stack with DRAM refresh also, but there's even more room to cut across the stack over here. Okay, so this is the paper that talks about parallelizing refresh and accesses. So let me talk about this paper also. So this is actually a paper that was written 2 years after we wrote Radar. This is a paper that was written by Samsung and Intel, and I also recommend this paper. It's only a 4-page paper. It talks about DRAM process scaling challenges. And it basically says refresh is a major problem, variable retention time is a major problem, just like we have discussed also in our papers previously. It also talks about write latency, saying that write latencies are increasing because of contact resistance between cell capacitor and access transistor increasing. Basically, I believe write latencies are less fundamental. It's also important, but I believe less fundamental because actually a lot of other technologies have this problem also. But refresh and VRT are really, really fundamental to DRAM going into the future. It's going to be much more difficult to solve the refresh problem and variable retention time problem in DRAM. Okay, so this paper also proposes what we have been proposing in our previous works, co-architecting controllers and DRAM to enhance DRAM process scaling. It's nice to see always your ideas being also proposed by very, very credible people from Samsung DRAM design team and Intel memory and DRAM design team. I actually know some of these people personally. Actually, I think I know all of them personally. But basically, these folks are designing DRAM circuits and also memory controllers. And they've been designing this for more than 40 years or so. John Halbert, for example, has been designing DRAM for more than 40 years at Intel. Okay, so it's basically, this also gives you a mindset of change in industry. So if you look at industry, people did not propose this sort of cooperative solutions across DRAM and memory control, across different components before. But this was a very forward-looking paper. And it actually cites some of our work, and it actually independently evaluates some of our work and shows that it's a good idea. And it gives it as an example for co-architecting controllers and DRAM. It's the work on sub-array level parallelism, which we may talk about at some point. But basically, it shows that the mindset in industry is also positive, and industry is open to new ways of actually designing memory controllers and DRAM together. Okay, basically, we will dig deeper more in this course, and basically, we will see that good ideas are a dime a dozen. Sometimes, actually, even though I believe this, sometimes I don't believe it also. Sometimes to get to the good ideas, you need to ask the right questions, and you need to basically exercise your creativity so that you actually get to those good ideas. But even if once you get to those good ideas, the work doesn't stop. Basically, making those good ideas work, once you've somehow determined that those ideas are worthwhile exploring, is oftentimes a real contribution. Actually, that leads to a lot of interesting work, and that leads to people employing your ideas in real life also. So I would suggest digging deeper and always asking questions in this course. Why? How can we do it? And Piazza is a good place, but of course in the lectures are also a good place, although sometimes I feel like I'm rushing too much in these lectures, but we're going to change that. But these are initial lectures, so hopefully in the initial lectures I want to set up the stage in a better way. But let me foreshadow something really, really quickly. You may think that, okay, DRAM, very specialized, it's going to go away anyway, so why do we care? And again, this is the naysayer's point of view. And you will always get this sort of criticism. Actually, it's really interesting. When our team was working on phase change memory, I got the criticism saying that, why are you working on phase change memory? It's not a real technology. Why don't you work on DRAM? And we also started working on DRAM. Because in the end, as a researcher, you really want to work on the best problems, right? We also started working on DRAM, and we got the criticism saying that, oh, DRAM is going to go away anyway. These are very specialized problems. Why are you working on DRAM? I have yet to see DRAM go away. I don't think it's going to go away. But also, there's also another thing that's really interesting over here. A lot of the things that I'm telling you about are really fundamental. They're not just specific to DRAM. Some specific incarnations may be specific to DRAM, but the high level, like charge leakage, randomness of retention time, how to solve the problems, they're actually very fundamental to other types of memory, and they're going to recur in other types of memory. One example is flash memory, for example. So it's not like DRAM, even if DRAM goes away, these problems will go away. Second is, the phase change memory, as we discussed, it's already real, right? It's good to bank on the technology and say, okay, maybe it's not going to go away, or maybe it's going to happen sometime in the future, so let's do the research to enable it. Okay, let me foreshadow something that we may cover. If we don't cover, then you can actually look at lectures from old lectures, old things. But I find this fascinating also. So charge memory is memories that store data as charge. Flash memory and DRAM actually are two examples of prominent charge memories, and they're everywhere in our lives. Flash memory enabled this, for example, which is my cell phone. I don't know if I'm sharing my screen. I guess I'm sharing my screen so you can see my cell phone more than once. So the cell phone is actually enabled by flash memory because that enabled us to actually have large storage on this form factor, right? So both of these memories are actually vulnerable to issues that are very similar: data retention and reliable sensing. So if you thought flash memory is non-volatile, think again, actually. Flash memory actually loses data over time. And it could actually be reflected in terms of latency degradation. So this is one example that we use in one of our papers. Basically, you degrade performance of an SSD significantly because some old data is very slow to read. Compared to basically 500 megabytes per second at the time, you read this data as slow as 30 megabytes per second. And this is because the data is not retained well. Basically, newly written files can be read much faster. So there's retention loss. So this is actually graphics from Yishin, who was my PhD student, who actually did his thesis on flash memory. So basically, in flash memory, you have a similar phenomenon. You get charge leakage over time. If you don't solve the problem somehow, you lose the data. Existing flash memory devices actually read the data much more slowly, doing error correction and other mechanisms. That's why you get the picture that I showed you earlier, only 30 megabytes per second read, as opposed to 500 megabytes per second read. So you could either lose the data or read it extremely slowly or add more error correction. So basically, retention loss is really one dominant source of flash memory errors, and side effect becomes longer read latency. So I'm not going to go through this in detail, but there are many other errors, but retention is actually one of the biggest errors. So we have a similar infrastructure that we built for flash memory over the course of years, and we tested flash memory chips in a similar way. And we found out that the retention time errors are the most dominant. You don't need to read the slide. You can read the paper if you're really interested. But these papers are actually seminal papers that are taught in industry to engineers who work on flash memory and SSDs so that they can actually design much better systems going into the future. But basically, we showed that retention errors are dominant in existing flash memories, and they actually increase with the retention time requirements. So, for example, if you store data for 3 years, you will have more retention time errors. if you have worn out your device, if you actually done a lot of writes to your device, you're going to retain data for much lower number of years or months actually. So if you have overused your flash memory, it's likely that it's going to lose data more. It's more likely that it's going to lose data. But if you're interested, basically, flash memory errors actually exist and retention time errors are dominant. This is the paper that showed that. So what is the solution? The reason I'm explaining to you all of this is basically the solution is to refresh periodically also. Basically, you change the period based on how worn out your flash device is, SSD. And SSD controllers, existing SSD controllers actually do this. We propose this in our paper that I'm going to reference. Basically, you refresh more frequently, more often at higher wear outs. For example, if your flash drive has worn out a lot, you refresh every 3 hours. If your flash drive is new, you just bought it, you didn't write anything to it, maybe you refresh every 3 years, right? And we actually show that in our paper. We have a gradual refresh whose period changes with the wear out that the device sees, so that we minimize the overhead of refresh. Okay, I'm not going to bore you with this, but there are multiple ways of doing refresh in device. You can remap the data to another location. You could actually do this in DRAM as well, but in DRAM it's very high overhead. In Flash, you need to do it for other reasons also. But basically, you could do a different form of refresh. And this was proposed in our work that was presented in ICCD in 2012. If you're interested, you can look at the paper. I don't know if we're going to cover about SSDs in this lecture. I haven't decided fully yet. If people are interested, maybe you can pose your opinion in Piazza also. But basically, yeah, you can read other papers also related to this. And clearly, there's a lot of interesting work that needs to be done to understand the data retention behavior and optimize even more. So refresh by itself is not a good solution, again, even in flash memory. Just like in DRAM we've discussed, refreshing periodically is not a good solution. So you should probably do something more intelligent about it by understanding the device characteristics and designing your SSD such that it's much more intelligent in how it handles these data retention errors. And this is not going away. At 3D flash memories, meaning 3D stacked devices, that's one way of scaling flash memory to very high densities. The problem becomes even worse, so you have early retention loss, and you need to handle it in a different way. And you can see some of these papers. Again, some of these have gone into Yukai's PhD thesis, and later Yishin's PhD thesis for 3D NAND flash memory. I find this fascinating, and some of you may actually find these error mechanisms, especially retention errors in this particular case, fascinating also. And if you're really interested in getting initiated into flash memory SSDs and errors and their mitigation, I would recommend reading this paper that we were invited to write as a result of our 8 years of research in flash memory. And we basically summarized our research as well as things that are going on in industry on how to build reliable solid-state drives. And I would recommend looking into this. It's a long paper, no question about that, but some of you may be interested. And my job as a lecturer in this course is actually to hopefully poke your interest in different places where you might be interested in. But of course, there is always a more up-to-date version of articles that we published, and this went into this Inside Solid-State Drives book, which I would actually recommend to people who are interested in solid-state drives in general. It's a fascinating world, and I'd recommend, if you're interested in solid-state drives, looking into that book, and this particular article is updated with our more recent work. Okay, and if that's not enough, and if we don't cover flash memory, you can watch it in these YouTube links, because these are actually our 2018 lectures. In 2018, I actually created special flash memory lectures because there was interest. We may actually go back to it again and enhance it this year, but it really depends on, let's see. Yeah, if you have interest, let me know also on this. Some of the things that we cover in this course may actually be guided by the interest from the participants, since it's a master's level course where most people are master's or students or senior level bachelor students. But if you're interested and if you cannot wait, I would recommend looking into these lectures, because we put actually a lot of care into preparing these lectures. And I don't believe anything like this exists out in some other open environment, talking about different issues in flash memory reliability and how to design reliable solid-state drives. Okay, again, as I said, we may update these lectures in 2020, but I'm not sure yet. Okay, I took much longer than expected. I apologize, but hopefully you can watch this on your own time at some point, and we're going to make it up later. Any burning questions before we pause? Okay, I don't hear anything, and I don't see anything. But I think what we will do is, please, 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 if you have questions or thoughts or anything related to the lectures, post your opinions on Piazza. I want this lecture to be as interactive as possible. Unfortunately, we're limited by the capabilities of what we're doing right now online, but at least we can make use of Piazza in the best way, and we'll try to schedule discussion sessions also where we can actually brainstorm more freely, assuming, of course, we have enough reason to schedule those sessions. I don't want to go into a discussion session and have basically no questions and basically call off the session, right? That wouldn't be a great use of our time in the end. So the way to gauge this is really people participating in Piazza and providing even short questions or thoughts so that we can actually discuss more freely in discussion sessions, and we can actually discuss online on Piazza also. Okay, so that's all I have, and I think I will see you next Thursday. And we still haven't decided the time for the lecture on Thursday, but we will communicate that after looking at the poll results. So if you haven't participated yet, you still have some time to participate. Okay, take care, everyone.